The organizers of this program, especially Keith, Conrad, Tom, who's here, and Yoshi, who's not here, and others who may had a part in inviting me here. And I enjoyed my visit here tremendously, and the symposium last 2 weeks ago as well. Well, this obviously is as the title suggests, is a crossover kind of project between physics and art. And I guess my only excuse for giving this talk is that there are, in fact, some topological aspects to the patterns and phenomena that I will touch on, and as you perhaps will be kind enough to notice somewhere. Let me acknowledge my collaborators, especially Mahadevan, as he likes to be called, or Maha for his friends. Pretty much everybody, that is. He is the principal collaborator here, and he is the one who's been the first to write scaling law for coiling instability, which I'm going to refer to. My good friend and professor of fine art at Boston College, Claude Chernusky, provided support in terms of preventing me from saying some horrible things from the art historical point of view. He's been working on me for a long time, trying to improve my understanding of art. And then David Martin did some calculations and image processing that I will mention at the end. And he used to be at BC, but is now at Google, making, I think, 10 times the salary, and working on some secret projects, including filming our streets and so on and so forth. Okay, so here's the outline. First, a little bit about the relationship between nature and art. Then there'll be 3 parts. Still a background part on port paintings, as art historians like to call them. A few notes on fluid effects and fluid dynamics involved, in particular the various jet instabilities. And at the end, a short part, I'll just touch on it, on scaling properties and perhaps some affinity to nature that these paintings represent. Well, artists have, or maybe I should start by saying that there is a wonderful ambiguity about the word art itself. Ars in Latin. On one hand, it refers to skills or craft or technique. So to things that are artificial or manufactured, as illustrated by this Mondrian painting, which is quintessentially artificial. That's its raison d'etre. On the other hand, it also refers to knowledge, to science, to character, as in ars technica or ars medica and so on. So to the nature of things, as illustrated perhaps by this Vermeer painting. In any case, it has been a long tradition in art to represent nature, going back to the very beginnings of art. And indeed, one strand that's been particularly successful is representing nature in stasis, that is to say, static representation of nature, as suggested by this master of the genre, Spanish painter Cotan. This is clearly a static image of nature. This one manages simultaneously to be very natural and very artificial, which was something of the skill that this particular artist developed. But it's a little more tricky to represent nature in dynamical case, as illustrated by this well-known painting by Scottish painter Raeburn, showing Reverend Walker supposedly skating on a lake. Now, or loch, as the case may be, yes. Now, the question can be asked whether he's in fact skating, or is he posing and not moving. The added complexity is that, in fact, to be represented as skating, he in fact had to pose statically. So there is layers of complexity here. So, well, maybe dynamic. Well, a better way of representing motion is, and a way out of this dilemma for artists, was to use deformable media, including, by the way, flowing drapery and things like this, which I'm not going to talk about, but including fluids, as in this well-known painting by Vermeer, where the flow of milk, the laminar flow of milk, reproduces pretty faithfully what milk stream in fact looks like. So this is quite successful. And it doesn't have to be laminar. It could be a vertical or turbulent flow. This is one of the series of Leonardo's drawing, remarkably faithful to the actual vortices and turbulent behavior that may be seen in fluids. Okay. Well, another possibility are waves. Here, the absolute master of representing crashing waves was Courbet. This is one of many paintings that he's made. I've tried to find a reasonably similar picture of the real thing. So in all of these examples, art is used to render fluid flows. But it's altogether another matter when fluid flows are used to create art or to render art. This is just the flip side of it. And my talk is going to be mostly on this. But before I get to the main actor, Jackson Pollock, let me say that there are many ways to do this. One is using rivulets, as in Maurice Lewis' painting shown here. I'll say a little more about this, but basically he folded his canvases and let paint of various colors flow down. Another is by sprays, flicking essentially the paint-laden brush, as in this painting by Robert Motherwell. Another is just using drips by themselves. And here, when you say to art historian who is the drip master, they will not say Pollock, they will say St. Francis. So here is the painting of his. And finally, yes, pourings, that is to say free gravitational flows falling on a canvas that Pollock engaged in. And here's an example of his painting that I'm going to return to. All right, so first part, I'm going to start with describing Pollockian mechanics a little bit. Contrast jets with drops. Talk about transition between the two, and then contrast it with some other gravitational flows that may be used to paint. Well, a few facts about Jackson Pollock himself. Born in Wyoming, moves to New York as a young man, studies with a well-known teacher of many great artists, Thomas Benton, and worked for work project administration. That's all fine. And then real change occurs when he marries painter Lee Krasner, and they decide to move to a small little town on the eastern edge of Long Island, where he has a barn, and in that barn he starts pouring paint. Soon after this becomes famous when a Life magazine publishes a big article about him. This photo is in fact taken from Life, from that issue. But this is the so-called classic period from 49 to about 55 maybe. Very short. And then he dies in a car crash, killing yet another person, one of his mistresses, before having time to. So lived only 44 years. The main thing to know about Pollock's technique is that he changed the way the pigment is delivered to the canvas. Namely, he placed the canvas horizontally rather than vertically at some small angle on an easel. So the canvas comes off the easel and on the floor, and now he pours paint onto the floor, in effect engaging fluid dynamics in the artistic process itself. and thus, I claim, opening his work to a fluid dynamical analysis. Here's one of the well-known paintings, which is near monochromatic, that is to say, sort of white and black, showing the tangle of lines, pretty dynamic looking. I don't know, perhaps this is the result of relaxation process in some MHD situation, or maybe not. In any case, the point I want to make is JP did not just depict liquid in motion. In fact, he did not depict liquid in motion. He set liquid in motion to produce these things. And these two photos clearly show the dynamic process that's involved. Well, better than photos, perhaps, is to look at a film. This is one of several films made by Namuth, 51, showing how he did it. Contrary to popular belief, he didn't pour paint out of a can. He dipped a stick into the can of paint and then let it dribble down in a stream, but occasionally also engaging in spraying kind of motion that you see now. Okay, that's probably enough of that. He liked to say, and he repeated it a number of times in various ways, that there was no accident. I can control the flow of paint. There's no accident, just as there's no beginning and no end. I'll let you judge this for yourself. So here's some of the results. In here you have mostly jets, that is to say these continuous jet traces or skeins, but also many drops created by spraying or otherwise. In this painting, there are mostly jets and very few drops. There are some drops. There are jet skeins that are white and black on some, I don't know, beige background. And here, by contrast, is what the painting would look like if you had mostly drops. So I've mentioned already San Francis specialized in drops. This looks very static, and in this case, somewhat contrived. This looks dynamic. Things are happening, and it invites further investigation.
To my eye, this looks very three-dimensional.
That's right.
Same impression?
That's right. That's right. So, art historians often say that it appears as if you had some kind of three-dimensional structure, and some people say that it even appears to be moving or just about to move. By the way, please interrupt at any time, and if you want to see any paintings for a longer time, just stop me. Okay, so this is San Francisco. Now, of course, there is a transition, or there may be a transition between jets and drops, particularly through capillary instability. So here is a nice paper showing some experimental result with the droplet breaking from a stream and some ligament created and satellite droplets and numerical simulation. Or else you may produce this effect by, for example, using a pipette, drawing some liquid, letting it go, and it starts as a jet of some kind, also in this case in a finite length, and then it breaks in a typical fashion, that is to say, into the main droplets, and then ligaments that break themselves into small satellite droplets, and so on. So certainly this process has also been occurring while Pollock was painting. But perhaps the best illustration of this is in Motherwell's paintings, I've mentioned already. So here, I should say that these large black areas were painted with the brush, but everything else here this is, for example, presumably flicking the brush laden with paint, and here, if you look carefully, you can see jet breakdown, and even better here, my favorite painting, where you have the main droplets and the satellite droplets and the ligaments. So this is as if Motherwell caught capillary instability in flagranti, so to say, right here in this painting, and there and in some others as well. Let me contrast this with the surface flows that I've alluded to briefly before. This is the same painting by Morris Lewis. I've already talked about this, created by folding the canvas and then letting the paint stream down. By the way, Lewis was extremely protective of his technique, so nobody has ever seen him paint. Well, I don't know, maybe his wife. So it's not known exactly how he did it. This is another version where there were blobs of wet paint at the top in this Pat-Steer painting, and then she moved it around, and the wet paint streaked down gravitationally along the canvas. Very different effect. This for sure, and this also from the Pollockian dynamic three-dimensional or quasi-three-dimensional result. By the way, there is one painting by Jackson Pollock that has similar effect. So presumably this was created by accident. There was a wet area, I think, of black paint here, and he didn't wait. He was always, as soon as he finished painting, by the way, he repositioned his paintings to wall to appreciate them. And apparently he didn't wait long enough. So some streaks were created, and then he decided, well, that was okay after all. So he left it. So this is one known example of similar effect. All right. Let's talk about the fluid effects, the basic physics of painting. So first about the viscous adhesion to pull paint out of the container in the way he was doing. Dispensing paint, well, the impingement of stream and therefore cooling instability that may be created in some instances. I'll say a little bit about the traces themselves that result from this. And as an aside, a little note about the reverse scenario. So in the Pollockian scenario, the jet origin is being displaced, and the jet falls on a stationary surface. In this reverse scenario, the jet origin is fixed, but the surface on which it falls moves. All right, so Navier-Stokes equation with the body force being the gravitational force. So here's the geometry. Cylindrical rod is being pulled with a constant speed out of the viscous liquid. And we're going to simplify it vastly by first assuming there is just a z component to the flow, no azimuthal or radial flow. The continuity equation then takes care of this term here on the left-hand side. And if you assume steady state, the whole left-hand side goes. And this is roughly what you get. And basically, this means that the scaling that governs the thickness h, shown here, of the liquid, viscous liquid being drawn by viscous adhesion, scales as so. This is essentially a balance of viscous right, and gravitational forces. So one can estimate the thickness of the layer being pulled.
In fact, the thickness varies with height.
It does. It can, but remember, we're trying to, of course. So yes, and also he doesn't have a completely cylindrical tools, and he doesn't pull them vertically up, and so on. So this is just a simple, very simple model for what this may look like. So continuing with the simple model, suppose now you stop the process and let the jet form. Then you can write a flow rate in terms of the thickness that I was just talking about, the radius of the rod. Substitute this simple scaling and obtain an expression for the fluid flow rate. Interestingly, it increases with the viscosity, also weakly, because the higher the viscosity, the more liquid is entrained, and so more to flow down, increasing the flow rate. A note about the shape of the jet, also a very simple analysis here. We've been criticized, by the way, for this drawing by some letter writers to Physics Today, telling us that it never looks like this. The jet never looks like this, but it does look like this sometimes. For example, here in honey, it pretty much look like this. But anyway, so
You're saying it should have a neck. Is that their argument?
no, their argument was so that they took a can of paint and chopsticks or something and made a film, and it showed that it goes like this, very close, like this, and the argument was that this is what it looks like, and it will never gradually transition to a thin thread, but I mean, it does sometimes. I mean, there's no dispute with it. Anybody can do this experiment. So it depends basically on viscosity. The simple answer is, yeah, if the viscosity is low enough that this may happen. All right, so the flow rate down the jet, a little distance down where the radius of the jet is r, maybe written like this. Again, we write a very simple balance of gravitational and viscous forces. From this you obtain this estimate for the radius of the jet as a function of its length. And yeah, you can normalize it with the initial radius of the jet at the origin, and you obtain this result. Now, here's Niels Rieb's full calculation as a function of the Reynolds number. Let me focus on this curve first. So the quantity, so here is the ratio of the radius. He uses A1 for that, normalized by the initial radius, so the same quantity as I have. But he plots versus what he calls effective gravity, which is this quantity squared and inverted. So inverse square of this is this. And this is a log-log plot. So the first thing to note is that for sufficiently large h, let me say, sufficiently far down this axis, maybe past about 100, this being a non-dimensional number, you have a straight line with a slope of -1/2. And so this behavior here is this behavior. So this very simple analysis reproduces, and this is numerics with the full Navier-Stokes. So it reproduces the far away behavior down the stream. Obviously, as the h decreases to 0, somewhere here, or farther down, in fact, then it needs to asymptote to 1, since r over r0 will be 1 in this case, obviously. So yeah, so there is a transition. So this is pretty obvious. This is captured by that, and then there is a transition period that this very, very, very simple analysis doesn't show. And by the way, here is the increasing Reynolds number. So one can think of this as let's say this plot is essentially where viscous effects can be ignored, and this is the well-known -1/4 inviscid result. All right, so this is the shape of the jet. So much about this part. Now I want to go on to the instabilities. And we first noticed in this painting, I was sitting in my office with a good reproduction of this painting, and I started to see these little oscillations everywhere on these lines. And I started to puzzle about it, and my collaborator, Claude, said, "What? Yeah, there are oscillations, so what?" And I said, "But there are oscillations all over this thing." And then I realized, well, this must be calling instability, my God. So let me show you some magnification of this. I will show you 3 details, 1 and 2 immediately, and the third one later a little bit. And so here they are, 1 and 2. And you can see that these are quite regular, in fact. They're the art historians think either that these are completely unimportant and who cares, or they say, well, yeah, obviously he shook his hand in a regular way. I don't think so. He didn't shake his hand to produce this. And these are very small. These are the radius of some of these is about 2 millimeters, maximum 3. So these are tiny, and they're all over the place. So we thought, well, obviously there are coiling instability. This painting is notable that for several things, but one of them is that it's on paper, a smooth surface. In order to see this clearly, you need a smooth surface, and so coiling is seen particularly well on works on paper. There was recently, 2 years ago, a Guggenheim exhibit on works on paper, and we made quite a stir there in Guggenheim by discussing all the coiling effects in various paintings. Another thing I want to say about this, there's two effects here. You have a diluted black ink that essentially you can see here, these little dendrites, that this diluted, pretty much invested watery ink just soaked into the paper. But this red traces are of highly viscous enamel paint. In fact, so much so that after it dries, it has this plastic effect, and you can see that the even thin threads of the black do not produce coiling. You need viscosity to do that. So yeah, this is like coiling flow of honey or some other highly viscous flow. Now, if you want to try to understand what kind of coiling this is, the first thing to say is this is a subtle effect. And till recently, aficionados of this field, like Neil Reben, his collaborators, were distinguishing 3 regimes of coiling. There's a recent paper this year where they distinguish 4 now. Now that they have worked out very carefully this interesting regime here. So basically, so first of all, let me say that this is a plot of the frequency versus the height of the jet. Both are normalized by these quantities made of viscosity and gravitational acceleration. And this plot is for silicon oil. And for silicon oil, it so turns out that these two values are about 10 hertz and 10 centimeters each, but it obviously be something else for different liquid. And yes, apart from this initial phase here, more or less the frequency rises with the increasing height, except there's something crazy going on here. Namely, you will notice that there are multiple solutions at some frequencies here. So the coiling can occur in 2 different frequencies, sometimes 3 or more, at least 3. And exactly what it does it depends on initial conditions and some instabilities and so on. So yeah, 4 regimes. At one end here is the viscous regime. This is like squeezing toothpaste out of the tube, where gravity inertia is essentially negligible. And the sort of the characteristic of these flows is this instability is that the radius of the coil is of the comparable magnitude to the height of the jet, as shown in this picture here. The other extreme is called inertial. Here, viscous forces and inertia balance, and gravity is smaller than either. And in this case, the radius of the coil is much smaller than the height of the jet, as seen in this picture. This is the height, and you can see the radius of the coil over there. Yeah, and then there's 2 transitional regimes. One that's been recognized for some time. It's called gravitational, or gravity and inertia balance. And this newly coined or named region called now inertial gravitational, which is transitional and stable and so forth. So the question is, these little oscillations in Pollock's paintings, which kind of coiling is it?
Is there some sort of period doubling going on in this new regime?
Here?
You know, is it close to chaos?
I don't think so.
I think there's just multiple stable
There's multiple states.
There's multiple attracting fixed points just in
Yes.
It doesn't have to have chaos, it just has 3 or 4 fixed points that attract them.
Yeah. So if you make basic measurements or estimates, so this is a measurement of the radius of the coils in the painting that I was discussing. Here is an estimate of what h, the height, the length of the jet must have been, based in part on photographs like this one, but also on other evidence. So probably in this region. So then you see that h is much bigger than r, and so at least in this painting, what we're dealing with is mostly inertial coiling. So the first person to look at this and write this scaling law for the inertial coiling was Madhavan. This is well, the original work was 98, but there's a little mistake here. They corrected it in 2000, and this now stands. And so this gives the frequency of the coiling as a function of the thickness of the thread in the, I should say, in the tail, flow rate, and viscosity. And you see that if you ask what's the frequency, then it goes with some rational but non-integer powers of these. So slightly strange-looking scaling law, but it basically comes from equating viscous bending torque and inertia with gravitational effects as well. And we've rewritten this in order to be able to make some conclusions, since clearly we don't know the frequency with which the Pollockian paint was coiling, but we know the radius of the coils and we know the thickness of the coils. So for these two quantities, one can, in similar way, derive these scaling analysis as a function, again, of the height, viscosity, flow rate, and gravity. Okay. So let's go back one more time to these values taken from Untitled 1947. And for one thing, you can eliminate h between these two, and if you plug this in, you find that the flow rate must have been somewhere in this regime from about 1 to 50 centimeters cubed per second, where we don't know the viscosity, but it's probably similar to the silicon wire. And then once you know this, you can estimate the range of h's, and so we've calculated that. So you can do a little forensic here and analysis essentially, and find out that probably the range of heights of Pollock's hands above the canvas must have been roughly in this regime. So that's nice. That's consistent with what we know about how he painted. Just to make a point, this is inertial coiling. Yeah.
50 cc per second seems very, very large.
That's right. But this is very large for large.
Whole glass of vodka in 1 second.
Yeah, right. So this is yeah. So
Lucky in the analogy.
It's mighty waste.
Only in Polar.
well,
Pollock was quite a good drinker, though.
Well,
yeah.
I don't think he would spill so much.
This is large. This, so a few centimeter cubed is just very common. So maybe this region was visited less. This is sort of a generous range here. Anyway, so speaking of extremes, on this plot, which is not normalized, so this is just frequency versus age, again from very recent work. Here's the experimental data for silicon oil. You can see that the frequency for even moderately high jets, 20 centimeters, can be very, very large. And just so you know that this is for real, here's a film showing honey dripping off a chopstick, pretty much the correct scenario. And you can see that this coiling goes bananas there. Probably around, I don't know, 50 hertz or something. And even higher in this case.
Andrzej?
Yes.
So, what is the physical mechanism of this instability, if you would
Well,
explain it in hand-waving manner?
So it's a bending force due to interaction with the substrate, where all these viscous forces and viscous torques and bending and so on
Okay, so
collaborate.
it never happened without the substrate, yes? You need to...
Yes, it doesn't happen without the substrate.
Okay, so the information goes back, so to say.
In fact, for these very viscous jets, if you don't have a substrate, you can obtain extremely long, stable, very thin threads that are not easily subject to capillary deformation. I'll mention this.
It's believed that the instability occurs when the thread goes into thrust, perhaps negative tension.
Deceleration.
Tension.
Decelerates.
Well, a bending of the stream, which behaves like a rope, due to the normal force from the substrate. By the way, so when you talk to physicists about this, the first thing they think of is the symmetry breaking. Right? I mean, this coil has to decide which way it's going to go, so this is for a physicist audience. I would say there is a spontaneous symmetry breaking in this.
Does it go either way?
It goes either way.
Randomly.
Randomly.
It doesn't depend on hemisphere.
Well, it depends. No, it doesn't. It doesn't depend on hemisphere. Just like water in I don't know, in a bathtub doesn't, contrary to popular beliefs. The scale is not right for the Coriolis effect.
But wouldn't you expect that if your substrate moves with respect to your chopsticks, that you then get some kind of different scenario?
Yes. I will say something about this in a moment. So if you can hold on for a second, I'll say something about this. So there is. I didn't bring it because it's still too large, but you can buy a toy, which is essentially a 2-compartment container with highly viscous liquid. There was a little hole, and you flip it around, and this thing falls and coils. That toy requires a little more physics to understand, because because the whole container is closed, the air needs to go from one compartment to the other, and that affects the flow, and so the flow rate changes. So what's nice about this toy, if you get a chance to look at it or buy it, is that it goes through all the regimes. And there, some of these toys have a tendency to coil in one particular way, I've noticed, and I'm not sure why. Perhaps that this has to do with the irregularity of the opening between the 2 compartments.
Because you turn it always with your right hand.
Well, maybe. So yes, you give it a little twist. Oh, yes, that's probably why. Okay. So anyway, we've discussed that. So yes, you've raised a point, or somebody raised a point about the stability of viscous thread. So in this paper by Eggers and Villermoz, they ask a question, honey, why are you so thin? Which I like. And in fact, Celeste Villermoz, Emile's wife, helped made this picture. These can be as long as certainly a meter or more, and in molten glass, as they say in this paper, they can be remarkably long, many meters long, 10 meters easily and longer. And they're not subject to capillary instability. And the question is, why not? One answer is that the growth of any perturbations that would tend to destabilize this flow is suppressed by viscosity, and Eggers and Villermo say that particularly at the onset here, it's important before this achieves high speed and the inertia effects become dominant. In any case, as far as I know, so it's not completely understood. The question is how viscous does this liquid need to be? And in this paper, Eggers and Villermo say they will publish soon an article that explains it, but I haven't seen it and I couldn't find it. Okay. So just to finish this coiling business, a little bit about the actual coiling traces. Of course, in the case of Pollock's technique, you have a superposition of coiling, which is autonomous with this lateral sweep of his hand. And so the result depends essentially on Strohal number, the ratio of the lateral to angular speed, essentially. And for small Strohal numbers, you get overlapping loops. Of course, Strohal number 0 is just coiling. For large Strohal number, you get some kind of undulating line. Straighter and straighter as you gets bigger, and then at critical value you get cusps, as shown at Strohal 1. And so in a sense you can read these paintings and deduce information about the speed of artist's hand. So here's detail 3, which I mentioned earlier, showing all three of these. So here, for example, cusps. And here cusps. Here are overlapping circles, even more overlapping here. And you can play games and you can follow the line and see that as he was navigating the stern, he was slowing down, obviously. These are now overlapping and speeding up, coming out, and so on. So you can do some posthumous analysis. All right.
Your discussion of that, with respect to a question that was asked earlier, implies that you don't think that the moving of the substrate sideways affects the dynamics of the actual coiling jet at all. It's just
No.
the impression moved.
So, no, I don't claim that, and I'm just about to say something about this. But what I'm saying is that in Pollock's case, his substrate is not moving. He's laying his canvas on the floor.
Relative to the end of the jet, it is. Relative to the source, it is.
No, but that's correct. That's correct. But the two problems are not symmetric. That is to say, you can't just transfer your coordinate system and say, well, this is the same problem. Can we postpone the discussion for just a moment? And then I'll come back to this. Anyway, I think I said everything there was to be said about this. But I want to add that I focused on one particular painting when these are particularly visible and prominent, but there are many other paintings. So we went hunting for coiling, basically. And so here's a well-known painting, one in the Metropolitan Museum of Art. And for example, if you look at this detail, there's some coiling right here and so on. And this is on canvas, so it's harder to obtain. But in this case, the paint is falling, the jet is falling on a locally smooth area after other layers of paint were there to sort of pave the way, literally, for coiling to be visible. Another well-known painting, number 1A, you take a look at this detail. There's some coiling here, for example. And I'll show one more. This is an odd painting. I don't particularly like it, and it's in private hands, so it was not easy to get this reproduction. But if you look at, maybe, there, at this detail, you'll see some coiling for it here and here as well, and so on. All right, so there's been discussion about moving substrate. I'm making a claim here that the two scenarios are not equivalent. And so this is recent work showing an experiment with the belt speed indicated here. Belt is slowing down. Initially, nothing happens. Then you have undulating lines, something people now call meandering. That's somewhat resembling of the coiling gaps you've seen. But then things happen that you don't get from coiling, and you're just about to see them. So there's these figure 8s that are created that you don't obtain from coiling. And as you slow it even more, there's some transition period. By the way, especially in this region, it looks like fluid dynamical stitching indeed, as if you had a needle going up and down. But in any case, after this little transition period, eventually it settles to these loops that you've seen. So this regime is therefore called coiling. But it's clear from the variety of possible solutions and fluid behavior in this case that this is not an equivalent problem. And the reason it's not an equivalent problem.
Interesting, isn't it?
Yes. I don't know what happened here.
Some symmetry breaking going
There's some symmetry breaking going on. I don't know if the film is now also inverted. But in any case, the difference is where the forces are applied. When you accelerate the origin, there the physics is different than when you push on the tail of the free tail of the jet. Okay, so not the same problem. All right?
No.
Yep.
I have the impression there is some effect of torsion, because the first loop comes down saying clockwise, and the next one comes counterclockwise, like it would somehow compensate for torsion in a certain regime of your.
Perhaps there's a twisting going on for sure, as there is in coiling, but why it switches from one orientation to the other, I don't know. I don't think anybody knows. But this is very new work, and papers are being produced as we speak. Anyway, a few words, if I may, about the finished product, so to say. I don't want to dwell on this, but since this is a topological fluid dynamics, I want to say a little bit about the scaling properties of the paintings and about our calculations where we fine-tuned scaling analysis a little bit. This is work done some years ago with David Martin, and a little bit about this affinity to nature business. So this whole field, so to say, of thinking about Pollock's painting as possibly fractal came about when Richard Taylor in 1999 published a series of papers, first in Nature, then in another that there are about now, I don't know, 15 of them, very similar one to another. What they are saying is that Pollock's paintings are fractals. There's a statement, and not just fractals, but double fractals. That means that on these scaling plots or log plots of the number of boxes, let's say, versus the scale, you have two regimes with two different slopes, essentially. And so they call one of them a drip fractal. So this is presumably connected with the fluid instabilities of the kind I've mentioned. And the other one connected with these quasi-random motions of the arms of the artist, which they term by similarity to Levy flights. They call Levy fractal dimension. So here's some of their results for one of the sort of monochromatic painting, which is the best laboratory to do this. And they provide two numbers, the D1, this smaller scale number, and D2, the higher scale number. Their higher scale number is almost always 1.9, so it's meaningless, basically. But anyway, and this is the painting I've shown you before, and they've provided these numbers, and they've done it for other paintings. Well, up to here it will be okay, but they started to make pretty broad claims, in particular that these numbers changed in a regular way as Pollock refined his technique, so that they can in fact date the paintings based on these fractal numbers, especially this D1. And then when there was some controversies recently, they're continuing about authenticity of some of the paintings, since they're, as perhaps you know, Pollock's paintings now fetch the highest price of any artist. He beats Rembrandt and so on in this domain, in the domain of finances. In any case, but it has to be Pollock to have this value, and so they claim also that they can authenticate the paintings by these numbers. So, but I am in the group of skeptics, caveat emptor, and in fact there's been some pushback, particularly by physicists at Case Western, Matur and his collaborator John Smith, Harsh Matur and Kate John Smith, and they published a number of papers. These are two of theirs on this topic, in which they essentially dispute the results. So here's some points they're making. The first is that there's simply insufficient range of scales to establish double fractals. In other words, even for the largest paintings, from, I don't know, a few meters to a millimeter, you get too few orders of magnitude to say, well, you have two straight lines on a log-log plot of scale. There is an issue which they spend a lot of time on, particularly in this PRE article, about the fact that you're talking about multicolored paintings, and if one color is a fractal, exact fractal, and another one is exact fractal and has some other fractal dimension, and now you put it together, then this is not going to be a fractal. They construct good examples, and so there's been much dispute about this. And then I think the devastating blow is this: Kate, John Smith, created some doodles in 5 minutes and showed that the Taylor criteria for authentication, in fact, are satisfied by the doodles. On the other hand, well-known Pollock's paintings, some of his well-known paintings do not satisfy the criteria. So this is really out, I think, although Taylor and company didn't acknowledge defeat yet. Well, our approach, as I said, we've worked on this some years ago, was to first of all refine the technique and develop a technique where we not so much look for obtaining straight line plots, but in fact look at the scaling plots and scale dependent characteristics, or local fractal dimension, as I call it. And we also, to avoid this problem too here, focus exclusively on monochromatic or quasi-monochromatic paintings, those that can be transferred into monochromatic mode. We think that having debates in nature about whether these are fractals or not fractals are pointless. After all, so suppose they are fractal, and then what? Okay, so suppose they're not fractal, and then what? Nothing follows from this that's interesting.
Well, it's not even a well-defined term.
It's not even a well-defined term, so who cares? But these debates are raging on, and we just completely, instead we ask, well, what do these scaling plots look like? Maybe there are some regularities in them. That's a better question to ask, and then you can ask if there's any insight. And certainly, we wanted to leave authentication to art historians. All right, so we used several different fractal dimensions. This is a standard capacity or box dimension. The usual covering of the pattern was the squares of some size and counting the numbers and so on. So for example, for Sierpiński gasket, you obtain this kind of a scaling plot. And if this is a real fractal, and this is a real fractal, except that the image is not a real fractal because the image has a finite resolution. And so if you look at the slope, here there's some little oscillations here, numerical oscillation, but they converge to the well-known fractal dimension of this. All right, so, but we fine-tuned this method in order to be able to essentially take a derivative of this log-log plot. And that's done by dealing with the boundaries. I don't want to dwell on this, but it turns out that when you do these coverings with boxes, what happens is the boundary is very important. You wouldn't think so, but we've spent a lot of time dealing with this. And so you have to compensate for the situation where the box, the mesh box, sticks out of the pattern into the non-pattern. There's a question of averaging. In order to take these derivatives, you need to average over grid locations. I don't think Taylor and company are doing this, but I don't know, since they don't say. And then there is a question whether you should average over rotations. We've taken an attitude that yes, that whether you hang a painting upside down or right, it should have the same fractal characteristic. In fact, in case of Pollock, this is a good idea since he changed his mind sometimes about how to hang his painting. So anyway, so we average and then we train our method. So this is a Sierpiński sponge, if you want. Yes?
Paint from different directions. Was he always painting from the same?
No. The canvas is on the floor and he walks around.
So he went around.
He walks around, but he almost never stepped into his painting.
Probably a good idea.
So which meant that the paintings couldn't be larger than something, his reach, and actually we calculated how big that reach is, and lo and behold, the largest painting that he ever painted is at the limit of the reach. But in any case, so we also trained our method on various what we call synthetic examples. So this should behave. So this is a plot, a scaling plot, should behave pretty much the same as this, and it does, and so on. So before I show you what Pollock's painting looked like, just what something else looks like. So we took a look at the noise. In this case, so the set of randomly distributed small dots. So here they are. So here is a scaling plot. This is the regular thing, and then we take the derivative, and the exact nature of this plot depends on the size of these things and the density, but pretty much this is what noise looks like on these scaling plots. I don't know, Taylor probably would say that there is a fractal here and there's a fractal here, but in any case, that's what this looks like. So now let's take a look at a painting that's a prime candidate for this analysis because it's large, very fully developed. It's a mature work near the end of his life. It's called number 32, and it's nearly monochromatic. Still, you need to convert it to fully monochromatic. And this is actually a non-trivial process to decide what is part of the pattern and what's not. It takes a lot of time and care. It's called thresholding, essentially. And here is the thresholded image. So this is the regular. This is the thresholded image where we decide what is black and what is white. And here's the plot. So there is some kind of a behavior at the low scales. This is essentially meaningless. Because if the scales get too large, let's say you have a box the size of the painting, obviously there's going to be some part of a pattern in there. So these plots need to go to 2. So this is not meaningful, but the transition, how it transitions, is meaningful. So I think what Taylor is thinking is there is one fractal dimension. I don't know, there's another fractal dimension, but it's nonsense. What you have some kind of a behavior, and this is the scaling behavior that this painting has. And we looked at some other paintings. We didn't do the comprehensive study, but we want to reformulate the question, as I said, and to ask, well, are there some discernible scaling regularities. So here's another, I'll just show one more example. By the way, the authenticity of this painting is in question. But anyway, here's a thresholded image, and here's the scaling plot. It's pretty much similar looking, starts at some moderate value of 1.6, and it goes to 2, it's the shape like this. So what about the affinity in natural forms? Well, one of the disputes that's in the field are things like trees fractal. Again, strictly speaking, they're not, but we took an aim at a tree. We call it an ABC tree, which means ABC tree. And then you threshold it, and there is a thresholded image of it, and you subject to the same kind of analysis, and lo and behold, something similarly looking appears. Now,
you did that just on the projected.
yes, this is a two-dimensional projection of a three-dimensional structure. Exactly. Boston College tree. So, here is the number 32 next to it. You can see it's a completely different thing. There's no attempt to mimic nature, but yet there appears to be scaling affinity with naturally occurring forms. Now, here are two quotations from Pollock. Not an illustration of, but the equivalent, his famous phrase. And also he said, my concern is with the rhythm of nature. So maybe he was onto something after all. A little caution not to overstate this. Here's a painting that's not very well developed, not particularly interesting, and figural, not abstract. And if you do the same kind of analysis, this is what you get. It looks completely different. So yeah, this has to be taken with a grain of salt. This is art, after all. There are different behaviors in different systems. All right. So if you allow me, I'll conclude. First, Pollock's technique, especially I'm talking about the classic, so-called classic period, is better described as jet paintings or stream paintings, and not the commonly used drip paintings, since the drips are accidental and play subsidiary role in the overall impact that these paintings make.
It's not easy jet.
It's not easy jet. It's quite non-easy. I didn't talk really about this, but Tim's question partly alluded to this, but we have essentially a record of these traces, but we have a record of three-dimensional dynamics in two-dimensional plane. Fluid instabilities, capillary and coiling, contribute fine detail at small scales, and you can do a little bit of investigation to learn something about these works and how they were created from the details of these smaller elements. I didn't mention it, but Pollock adhered to the so-called all-over idiom, meaning that he tried to avoid centers of attention in his paintings. And so this idiom, together with the spontaneous dynamics of his motion at various cases, leads to qualitative scaling regularity that in at least some of his paintings. And not to overstate the case, but poor abstractions do not illustrate, but through the scaling affinity invoke perhaps some of nature's effect. And I want to finish with a quote from Voltaire, who said, "Le secret des arts est de corriger la nature." The secret of the art is to correct nature. All right, so I want to also thank to art historians, Case Western, and the rest, my colleagues at Boston College, physicists, Harsh Mathur, Patrick Weidman, Howard Stone at Harvard, and my colleague Krzysztof Kempa. And there was a lot of help from technical people and library resources people at Boston College. So I'm grateful to them and grateful to you. Thank you.
Great, thank you. Yes, Tim.
Just if you forget about the fractalness, has it been possible? Is it possible to identify fakes using the regularity, Pollock's regularity, and you find one that superficially looks like a Pollock but isn't? I mean, that was the original claim of the Taylor mob. Is any of that justified?
So you will get a different answer from different people. I can only give you my answer. Yes, my answer is evidently not, since there are paintings, even with amazingly good provenance, namely from the storage that was used by Lee Krasner to put Pollockian paintings in. Paintings came out of this storage, and the art historical community is divided whether these are by Pollock or not. Some claim that these were exercises done by his students, that he didn't really have many, but apparently some people he played with, I don't know, and had them do something. So I think the evidence is not, at least in the art historical community. I don't know of any scientific way of distinguishing. I doubt there is. And you know, in art in general, once somebody does something, other people can copy it. For example, if you want to paint a Mondrian, you can paint a Mondrian. It will be as effective as an object, as an art object, as Mondrian. It's just it's not going to be a Mondrian. And well, that's a whole another dispute. But once things are done, other people can do them. And this is why artists always want to do something different. But that's my answer. I don't think, so the short answer is I don't think so.
Is there a way to incorporate the one-dimensionality? I mean, so if you just do random dots in box counting dimension, you can just make random dots with those dimensions. But the characteristics of his paintings are the linear structure, which are completely ignored. You know, these lines, I mean, it's just not dots filling in boxes. There's some spatial linear structure. So there's some one-dimensional scaling that's happening in spatial that's being completely thrown out. Are there tools to put this in?
You want to say something?
I had a comment on along the same line. It seems to me that the natural tool to analyze these paintings would be wavelets.
Yeah, so point well taken. Fractal analysis doesn't care if these are linear or not. I haven't thought of using wavelets for it. Maybe I should think about it.
Non-isotropic wavelets would, I think, capture some of that.
One could do other things with a picture. You could do a scan and construct the spectrum, just as you do with turbulence. Mm-hmm. The spectrum of the pattern, and it's two-dimensional pattern. And it's possible that that spectrum is characteristic of the artist. But there are other measures. And I was wondering on that point, this question of whether the picture is statistically isotropic. You know, he walked around, but he didn't walk around at uniform speed, presumably. He would pause now and again and get an effect. So the answer would be to place a circular canvas on a nice round rotating table and adopt the technique. Stand still and just work on for half an hour or so and let it rotate many times. And then do the analysis and see if it makes any difference.
Yeah. So,
but we don't have Jackson Pollock to carry out this sort of.
No, although I can. Good.
Can we drink the same amount?
Good point. I want to say there is one round picture. It's called, not surprisingly, Tondo. But it wasn't rotating. It was stationary, and he walked around.
But if I understood you right, you say that there's a difference whether the substrate moves and the painter is stationary or vice versa.
That's right. So the Moffat scenario was the rotating ground canvas would
It
take
does
us
make a difference.
out-
There is a difference at the point of release.
That's
if
right.
you're- If you're moving.
That's right. That's right.
But we
But-
did do some work on this here in Cambridge. I don't know if you know John Lister.
Well, I know, and some of the work I was referring to is his work.
Ah, yes. Well, he'd be, but he's not here, is he?
Uh,
I think Conrad was dining with him last night.
Indeed.
So he's certainly around, and we ought to tell him about it.
Yes, I'm aware of his work. He's been one of the pioneers of this fluid dynamical stitching.
I could just add one of his famous comments related to your last thing. Someone asked if nature was in paintings. He said, "No, I am nature. I don't have to depict nature. I am nature."
Yes, that's true.
Which is your last comment, that he had, the fluid mechanical phenomena had to be illustrated by his motion. He was working in the natural world. And he was illustrating nature because he was nature.
That's right.
Well, if we're talking about the philosophy of painting, I mean, you began with about what is art. Well, there is a famous textbook, I think, written in the 1950s by Ernst Gombrich called The Story of Art. And most of our past generation have learnt from it. And his first line is, "There is really no such thing as art. There are only artists." I mean, in some sense, you're illustrating that point because, I mean, his point was that people have been doing art since cave paintings,
Yeah.
and they didn't recognize that there was such a thing as art with a capital A. It's what people do.
Yeah.
And what you're doing is the physics of what people do.
Yes, although I would hesitate to extend it to too many other artists. So I have nothing to say about Rembrandt. Well, maybe I have something to say about Rembrandt, but I don't have much to say about the physics of Rembrandtian technique.
But yes.
Regarding unique signature of his works, maybe you can do something like consider painting as a manifold and look for spectrum of Laplacian. So in a way of Mark Katz's approach to can you hear the Pollard's paintings? That's
Well, it's a nice suggestion.
Can you hear the sound of a painting?
yes, that's combining both visual and audio.
Yeah. Well, I don't know. We haven't tried. I mean, that would be interesting to do, but not really to, in my perception, to try to get tools for authentication. I don't think it's. You have to decide what's an interesting problem. I don't think it's an interesting problem for a physicist to authenticate art, but I may be wrong about this. Maybe some physicists are interested.
Money in it.
Yeah, there's money in it. There's certainly.
Well, oh yeah, please.
I think there are two processes going on. One is to paint one line, and the other, the fact to put together many lines. And so, when you do a fractal analysis, you mix both together. And instead, if you would trace one line and then analyze these lines separately, you might get different information.
Well, I think this is what Conrad was saying, and
So, for example, we are doing a lot with DNA, just tracing DNA and then use like polymer theories to measure fractal dimensions, distributions, end-to-end distance distributions, and all this kind of information that you can get out from the single. One problem that you already said is the scale of the system. So there are not enough decades to get reliable quantities. Maybe the distributions of end-to-end distances or angles distributions as a function of distance and stuff like this.
yeah, I guess one could do a lot of things.
Yeah.
But I think tools that have some statistical component of the kind that Phil and Conrad mentioned maybe would be better. Anyway.
I was really puzzled by the fact that some parts of the painting make an impression of 3 dimensions, and some other parts do not. And the question is, what is the characteristics of a collection of lines that gives you this impression of being a projection of the three-dimensional object? Well, some other collection of lines does not have this effect at all. And
So he used
to
different
begin with,
colors. He used different colors in some of them, and
Use different
overlaying
colors.
different colors
Yes.
gives you
And different shades.
to begin with, the first thing to test would be whether the impression is the same for different people, because perhaps it isn't.
Yeah.
Well, it might depend on which glasses you're wearing.
It's good on your side.
I don't have an answer to this, but I think it's important to know that there are different shades of colors, and in human perception, for example, if you look at the landscapes, the master landscapes from, I don't know, 16th century, you will see that the faraway objects become light bluish. All right, so there's certain colors that project dimension, third dimension. Also, very visibly in many of his paintings, you see crossings of the line. And you see that there is, let's say, a black line on top, and there's a red line, and red line is on top.
Yes.
And I think if you have a mesh of these lines where you can clearly discern multiple crossings,
Which is behind.
it's what is behind what is in front, that it adds to the three-dimensional.
But a similar effect is with superposition of random plane waves with the same wavelength. When you take many of them independently, you see a similar effect that it is strikingly three-dimensional.
There are these examples of wonderful images where you have to sort of defocus. They look random, but you defocus your eyes and you see it. You then
The
see it.
stereograms.
What are they? They're stereograms, in effect.
Yeah.
Yeah.
I saw in New York in the window of a shop the stereograms, and the crowd of fools who were trying to see, and from time to time one of them exclaimed, "Oh, I see it."
Yeah. Yeah. Well, I think this is a wonderful example of the great, extraordinary range of fluid mechanics, applications of fluid mechanics, and really very, very interesting work. Thank you, Andrzej.
Thank you.